Good morning, everyone. I'm Paolo Filippucci. Good afternoon. Yes, sorry. I work at the National Research Council of Italy from here, 10 kilometers from here, not less, probably 3. And we are here again to talk about precipitation with a different approach with respect to before. We are more focused on the daily precipitation, and there are a bit of differences that we will see now. So why? We have just seen something very similar on Jacobo's presentation, the water cycle, that it is not the same as when everyone here studied at elementary school, because we are changing it. There are a lot of process. There is the precipitation, the irrigation that is always more distributed, that is making a lot of local changes. So now we have a new challenge for our models and modelers to model the anthropic intervention on the water cycle. And to do so, one of the most important part is the input data. So this is the idea behind this work to improve the input data that we can use to model and to understand our world. And in particular, we are focusing on precipitation. That is probably the most used forcing for most of the models. So how we measure precipitation? We usually use rain gauges and radars, of course. They are the most reliable source of data. And if you have precipitation from rain gauges and radars, use that. It is the best way. But clearly, they have limitation, mostly spatial limitation, because this is the situation here in Europe for two of the most used gridded precipitation data, EOBS and IMO products. And we can see that even if the Europe is already an area with very dense gauge data, we can see that there are a lot of holes in these patterns. We miss some data in the Po River Basin. We miss a lot of data in Spain. East Europe is practically empty. So we have to do something in the area in which we lack data. One solution is clearly reanalysis and models, but they often lack also the observation to work. So their output is subjected to several uncertainties. And then we can help those data with the satellite. Satellite, we can distinguish between two approaches. One, it is the top-down approach, let's say, that infer precipitation information from the atmosphere, from the clouds, like IMERGE later on, that was used in the previous product. And another is a bottom-up approach, where instead we use the inversion of the soil-water balance to infer precipitation from the variation of soil moisture, so the water in the soil. And we want to, each of those data of those products have its strength, each have its limitation. So we want to harness the mutual strength and improve our capacity to observe precipitation. So we have applied we can apply a tripod collocation analysis to multiple precipitation products. We can see the tripod collocation. It's basically a way to compare three products that are not biased each other, not related each other, against an unknown truth. And this analysis can say which is the most near to the truth. And we can see here from when we apply this analysis to top-down satellite, bottom-up satellite and reanalysis, something that is quite reasonable, because we can see that in all the north and south area of the Africa, in this case, where we expect to have more observations, ERA 5, that is the model, is the best performing. In the area here where there is the desert, and here where there is the pluvial forest, in which we cannot expect accurate measurement of soil moisture, iMerge Late Run, so based on the atmosphere, is the best performing product. And in the other areas, instead, SM Terrain has a big impact on the quality of the product. So the idea is to merge the product according to this kind of map with a weighted average according to the signal noise ratio that we obtain by the triple collocation. And we have done it selecting these three products, iMerge, Century NASCAT, and ERA5, that we select because they are globally available with low latency, and they are the ones with the best performances by themselves. We have downscaled them using the pattern from CELSA, just the pattern, a climatological pattern, one for each month, obtained by averaging CELSA, and to better distribute the precipitation at coarse resolution. And then we have used the weights to obtain this product at 1 kilometer and daily scale. Then we have to test it. So we have collected high resolution observation from rain gauges and radar in those areas, in the Po River Valley, in the Herold Basin, in the Ebro Basin, and also some data here in Austria. And we have also compared against other known data sets like the EMO, EOBS, CPC, gridded observed data sets, but also other satellite data sets like CHIRP, Persian, and GISMAP. So this is an example. We can see that we have two versions of our product, one based just on iMerge and SM Terrain, one that instead use also ERA5. We can see that already by the merging of these two kind of approach, we overcome, we outperform all the purely satellite product in terms of spatial correlation, temporal correlation, bias, and root mean square error. We are more or less on the line with the EOBS, with other gridded observed data. And if we instead put also ERA5 inside the merging, we outperform basically everything in this. This is for the Po River Basin, but we have similar results also in the other basin. So let's see why. This is an example here of the performance that we obtained for the Po River Basin. We can see that iMerge and SM Terrain by themselves have good correlation, but not so good. Merged, they compensate each other, even if we miss some information over the Alps. And with ERA5, instead, we got a very high performance that instead are missing in some areas for EMO, for EOBS, and for ERA5. Why? Because they lack observations. We can see that from these, those are the correlation of EOBS and of EMO against our high resolution data, and they are good performing where they have clearly their engages, where they have the observation. In the other areas, clearly they have to interpolate and they do some errors. And the idea is exactly to use the satellite to inform when they will be used, models to what happens in the meanwhile. So this is the same also for bias, for root mean square error, but let's see some application. We have applied this product and also other that we have developed with other partner in the Digital Twin Earth Hydrology project, in which we try to reproduce the water cycle at high resolution from satellite data and from models. So for multiple applications, we have water balance, water management, flood risk. There is a lot of things that I cannot explain now, clearly. We have several papers that are already available online, in which the dataset is used in multiple fields, landslides prediction, hydrological modeling, also groundwater estimation. So we are trying to test in multiple case studies. We have also something in the atrium, the work from Kalle Misetti. She has applied a MISG model, a semi-distributed hydrological model. They forced this model in the Po River Basin, first with the in-situ observation that we saw before, so radar plus pluviometers, obtaining very high KGA values. Then they tried to force it with iMerge late run at 10 kilometers with quite good results, but a bit far from the observation. Then they use this data set aggregated at 10 kilometer and the one at 1 kilometer. And we can see both the improvement with using more information from ERA5, from SM terrain, and also the improvement with the downscaling, with the theoretically high resolution, as Luca said before. And we have also applying in several other hydrological models. I will not go too much in details. The important thing is that we can see some improvement. They have applied all those models in the Po River Basin, in Rhine, in Tugela, obtaining some improvement for the Po, not many improvements in the Rhine, and some improvement in the Tugela Basin. But there are some, it's still a work in progress. Those are all they are not calibrated against observed discharge, or when they are calibrated against discharge, it is a weight 1/5, where 5 is given to the high resolution data from satellite of soil moisture, evapotranspiration. So we are still waiting for the final results, but these actually confirm what we already know. So that in the Rhine areas, the IMO forcing is already well performing because they have a lot of pluviometer and radar. In the Po River Basin, there are some gaps. In fact, our product improves a bit. And for Tugela, where we don't have practically any information, we can obtain very large improvements with the application of our product. So to conclude, we have developed two high spatial and temporal resolution precipitation product from downscaling and integration different satellite and analysis data. And we can see that already by just satellite, we have better performance than the other satellite products by themselves. And we can also see that we outperform the coarse benchmark in many plains and cultivated areas in which we don't have many observation, but we have worse performance over mountainous region. And adding the reanalysis increase our accuracy. The products are now being extended to all regions of Europe and Africa. This is almost done within the digital twin earth hydrology. So for all this area, we have 1 kilometer daily estimation from 2007 to 2024 daily. And now we want to continue our testing over the hydrological models, also by applying just the satellite data to see if ERA5 actually helps a lot, or already the satellite data can give us good performance, and we can rely on them. Here you can obtain further information about an article that we have published on ESSD. Here are the data for Europe region if you want to check them. And if you want some information about the digital twin earth hydrology, you can scan here. Thank you for your attention.
Let's see if there's some questions for Paolo. This digital twin earth hydrology that covers Europe at the moment, it's a European coverage.
Yes, but now it was the last phase that was over Mediterranean area, more precisely. But now in the new phase, we are covering the full Europe and the full Africa with several. We will develop the data set for all those areas, and we have also some science cases related to flood prediction and drought estimation and water balance in a lot of basin in Africa, Europe, and also an experiment in the US. Yeah.
Okay, and how does this new generation geostationary UMET satellite, how does this affect your work? The one that is now 15-minute, I think, and 2 kilometer over Africa and Europe.
Well, we will be
MG, I think it's called MGI or something. Then MTG. Yes. Does it affect your work positively, or is it opening new doors?
We will we will see. We are eager to test to test it, to improve it. We know that, for example, the downscaling using climatology from Celsa has some limitations. So we want to try to move to actually high resolution data like Sentinel-1. And so we are always testing to improve, but we are already quite
Any
satisfied.
other questions for Paolo? No? Okay, so we move to the next talk. Thank you, Paolo.